Hello and welcome to Unit 1, Lecture 3 for Introduction to Logic. We're picking up right where we left off. Last time we were talking about truth functional operators, and we learned about 5 of them: the tilde for not, the wedge for or, the ampersand for and, the arrow for if then, and the two-way arrow for if and only if. So we learned last time how you calculate the truth or falsity of a compound or molecular statement if you know the truth or falsity of the atomic statements making it up, the truth or falsity of the statement letters making it up. But what happens if you don't know the truth or falsity of the statements letters making up? Sometimes you can still know a lot about the truth or falsity of the complex statement. So let's take a statement like P arrow in parentheses Q arrow P, right? Suppose we don't know whether P and Q are true. We can calculate the truth or falsity of the entire statement by calculating the truth or falsity of all 4 of the possibilities for P and Q. So since there are 2 atomic statements, P and Q, there are 4 possibilities. P and Q are both true. P is true, Q is false. P is false, Q is true, or they're both false. Well, what we can do is we can make a chart by representing all 4 of those possibilities. So this chart is called the truth table. The truth table will have a column for every letter and for every logical symbol, and we'll have a row for each of the 4 possibilities. So looking at this table here, we're going to make 4 rows, one where P is true and Q is true, one where P is true and Q is false, one where P is false and Q is true, one where P is false and Q is false. Since the second P is the same P as the P we started with, we're going to give it the same column we gave the first P. So P is true in the first 2 possibilities, false in the second 2 possibilities. Once we have that chart set up, we can fill in the truth or falsity of the complex statement by doing the calculations for logical symbols. We'll start by doing the calculation for the symbol in parentheses. So looking at the 2 columns here represented in orange, true arrow true is true, false arrow true is true, true arrow false is false. Remember, that's the only time an arrow statement is false, when you have true on the left and false on the right. False arrow false is true. Once I know that, I can take that value, so I'm going to write under the column underneath that arrow I used to calculate it, and I'm going to take it along with this first column and use that to calculate the truth or falsity of the first arrow. So P arrow Q arrow P, true arrow true is true, true arrow true is true, false arrow false is true, false arrow true is true. So if I highlight that last one that I did, I see that that's the main operator of the statement. That represents the truth or falsity of the whole complex statement. We see it's true no matter what. No matter what P and Q are, if they're both true, it's true. If they're both false, it's true. If one's true and one's false, it's true. It doesn't matter. So it tells you this statement cannot be false. Logic alone tells you that this statement is true. A statement that cannot be false is called a tautology. A statement that's true for every possible combination of truth values to its atomic parts. That's called tautology. The opposite of tautology is called a self-contradiction. So that means it's false for every possible assignment of truth values to its atomic parts. So self-contradiction, the simple example is P and not P. See, if P is true, not P is false, so then P and not P is false. If P is false, not P is true, but false and true is still false. So we see that this statement is false no matter what. A statement that's false no matter what is called a self-contradiction. A statement that's true for at least one of the combinations of truth or falsity to atomic parts and false for at least one, so it's neither tautology nor a self-contradiction, is called a contingent statement. So it's true for at least one of its truth value assignments and false for at least one. So P double arrow, if P then Q is a contingent statement. We see again there are 4 possible combinations for truth and falsity. So either P and Q are both true, P is true and Q is false, P is false and Q is true, P is false and Q is false. We see that we do the calculations for the entire statement. I'm not going to go through that here. It's true when they're both true, it's false when one's true and one's false, and it's false when they're both false. So we see the statement is sometimes true and sometimes false. That makes it a contingent statement. So what we want to talk about now is how we actually do these truth tables. How do you do a truth table from scratch? What's the process like? You start by counting how many different statement letters or atomic statement letters there are in the complex statement. So you count how many different ones there are. If the same letter occurs more than once, we only count it once. Right? So there might be 2 of them, there might be 3 of them, there might just be 1. That tells you how many rows your statement has. That tells you how many different possible combinations of truth and falsity there are with atomic parts. Strictly speaking, the size of the table doubles every time you add a new letter. So we have all the old possibilities plus the new possibility being true and the new possibility being false. So that means for n atomic statements, you have 2 to the power of n rows. Now that sounds really complicated, but it's not actually that complicated. It means you need 2 rows if there's 1 statement. If there are 2 statements, you need 4 rows. If there are 3 statement letters, you need 8 rows. If there are 4 statement letters, you need 16 rows. We're not going to go above that. You don't need to calculate 2 to the power of n. Just remember that if there's 1, you need 2. If there's 2, you need 4. You need 3, you need 8, and so on. When you fill in the columns underneath the letters, for the first letter, you make the first half of the rows true and the second half false. And then you take those and reduce in half how many you do consecutively for the next letter, and you keep reducing until you get to alternate between TF, TF. So that sounds complicated. It's probably hard to understand in the abstract, but let's look at an actual example. Suppose we're doing this statement here. We're making a table for P or Q if and only if not P and R. So let's count how many different letters there are in this statement. There's P, Q, and R. There are 3 different letters. P occurs more than once, but we don't count 4. We count P once for the 2 occurrences of P. So when you have 3 different letters, it means you need 8 rows. So choose number of rows, I'm going to say 8. And the way you do this on the computer, you hover your mouse cursor over the cell you want to change, and you click that cell. You click it once to make it a T, click it twice to make it an F, click it 3 times to make it blank again if you have to change something that you did wrong. You want to start by filling in the columns underneath the letters. You start with the first letter from left to right. The first letter from left to right here is P. And you want to count how many rows you have all together in 8, and you make the first half of them T's. So I have 8 rows, so I make the first half of them T's for P. And if P occurs more than once, we'll make the P's the same. So we make this column underneath this P exact same as the column underneath the first P. Okay? Then you move on to the next letter, and you reduce in half how many you did consecutively. So we had done 4 consecutive T's and then 4 consecutive F's. If you reduce that in half, you're going to do 2 T's, and 2 F's, 2 T's, and then 2 F's. That's the only Q. You move on to the next letter, which is R. And again, you reduce in half how many you do consecutively. So half of 2 is 1. So it should be for the last letter you fill in, you always alternate between T and F, T and F. So 1 T, 1 F, 1 T, 1 F. When you have that filled in, you should have a row that represents every possible combination of truth and falsity for the parts. So we have one row, this first row where they're all true, the last row where they're all false, and in between you've got some T's and some F's. So the second row, for example, is when P and Q are both true, but R is false. The second to last row is when P and Q are both false, but R is true, so it's the opposite of that. Then you want to fill in the rest of the table, and you fill in the rest of the table in the same order you would calculate the truth or falsity if you were just calculating the truth or falsity of an atomic statement where you knew the truth or falsity of the parts. So we're going to start by inside the parentheses, and when you start by inside the parentheses, you want to start with the negations first. So I'm going to do this negation here. So this negation column here is the opposite of the column next to it. You can highlight the columns by clicking these boxes down here. So the opposite of this column would look like this. So we had true, 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 true. Now it's going to be false, 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 true, true, true. Right? Now I'm going to use that column along with this column for R to get not P and R. I'm going to write the not P and R underneath the ampersand for the and. That joins together the not P and the R. So false and true is false. False and false is false. False and true is false. False and false is false. True and true, though, is true. True and false is false. True and true is true. True and false is false. So that represents the truth or falsity of the whole ampersand statement. And that together with the Q, I'm going to use to figure out the truth or falsity of this two-way row. And again, the rule for the two-way arrow, when they're the same, it's true. When they're different, it's false. These are different. We've true on the left, false on the right, so it's false. True on the left, false on the right, so it's false. False on the left, true on the right. Sorry, this is false on both sides, so it's true. False on both sides, so it's true. True on both sides, so it's true. True on the left, false on the right, so it's false. False on the left, true on the right, so it's false. False on both sides, it's true. I'm going to use that together with this first column to figure out the truth or falsity of the or. So when one side's true, it's true. True or false is true. True or false is true. True or true is true. True or true is true. False or true is true. False or false is false. False or false is false. False or true is true. So this statement is sometimes true, sometimes false. That makes it a contingent statement, right? So we have this many truths and 2 falses. So on 6 of the possible combinations, it's true, and 2 of them, it's false. So we see that this is a contingent statement because if at least one of these under the final column that you do, if at least one of these is true and at least one is false, that makes it a contingent statement. So when you have 4 different letters, now I'm not going to do this entire table because it's really big. I'm just going to show you the answer, but it's got 16 rows. I'm not going to go through this all because it takes too long when we're doing doing this on the lecture. But the first letter, you make the first half of the rows true. So you make 8 truths underneath A there, and 8 falses. Right? And for B, you've got 4 truths and 4 falses, and 4 truths and 4 falses. For C, you do true, true, false, false, true, true, false, false, all the way down. And for D, you do true, false, true, false, true, false, true, false. Now, I'm not going to go through the combination, this entire table here, but you see that it's true for every possible combination. All 16 of the possible combinations is something true, so that makes it a tautology. The truth tables are really useful. You can use a truth table to do a lot of things. So one thing you can do, which we've just been going over, is I give you one statement. You can find out if that statement is a tautology, a self-contradiction, or a contingent statement. But if I give you 2 statements, you can compare those 2 statements to see if they mean the same thing. When 2 statements mean the same thing logically, we say they're logically equivalent. So 2 statements are logically equivalent when they necessarily have the same truth or falsity for every possible combination of assignments of truth and falsity to their atomic parts. So they mean the same thing. That means the same column for their final operator when you do truth tables for them are exactly the same. And we can test that by doing a truth table for the 2 statements. Suppose you want to know if not, in parentheses, P and Q means the same thing as not P and not Q. Can you distribute negation over a not? That's something people ask me a lot. We're going to answer that question now by seeing, does not both P and Q mean the same thing as both not P and not Q? And what we're going to do is we're going to set up a truth table for these 2 statements. And we set the truth table similarly like we did before. We're going to count the number of letters there are. We're going to count the number of letters in both statements. So P and Q, there's 2 different letters here. So that means we need 4 rows. The number of rows is 4. And we're going to set 2 tables next to each other, one for the first statement, one for the second statement. And underneath the first letter, we'll make the first half of the rows trues, and the second half falses. True, false, true, false. For the second letter, we'll treat this P the same as the other P, just like it was in the same statement. This Q the same as the other Q. Then we're going to fill in these tables. Now, we fill in the tables differently here because this is in parentheses, so we do the and first. So true and true is true, true and false is false, false and true is false, false and false is false. So that's the truth or falsity of P and Q. Now we use that column to figure out the truth or falsity of the not. So this was true, now it's false. This was false, now it's true. This was false, now it's true, now it's true. That's the truth or falsity of this entire statement. Now I can fill in the table for this other statement, but here, since there are no parentheses, I do the nots first. So this was true, true, false, false. Now it's going to be true, false, false, true, true. Now it's going to be over here for the not Q. It's false, true, false, true. Now these two columns I'm going to use to calculate the and. False and false is false. False and true is false. True and false is false. True and true is true. So the last column I did for each of these statements tells me what this statement means, right? They're both contingent, right? But they don't mean exactly the same thing. We see that sometimes they're both false, like in that first column. Sometimes they're both true, like in that second column. But if P is true and Q is false, or when P is false and Q is true, these statements are different, right? They're not equivalent. They're not equivalent because their final columns aren't exactly the same. They'll only be equivalent if their final columns, these last things we did here, this column here and this column here, they have to be exactly the same. They're not, these statements are not logically equivalent. So I answered no to this question. Let's do another one. So P arrow Q and Q or P, not P. Do those mean the same thing? We're going to do a table to find out. Now we're going to count how many different letters there are. There are two letters, P and Q. So we need 4 rows again. Take the first half true, second half false. True, false, true, false, true, false, true, false. This P we'll treat as this P. Now, notice that even though in this second statement Q came first, I treat it the same as the Q in the first statement. I don't do true, true, false, false for that one, for this Q here. I treat it the same as the Q in the first statement. And this P here, I treat it as the same as the P in the first statement. You set it up like one big table. You don't set it up as two tables when you're doing the letters, columns under the letters. True arrow true is true. True arrow false is false. False arrow true is true. False arrow false is true. Over here, we'll do the negation first. So this was true, true, false, false. Now it's false, false, true, true. Now we'll do this column underneath the or. We'll look at the two columns next to it. True or false is true. False or false is false. False or true is true. False or true is true. So we see when we look at the final columns we did for each of these two statements, it's both true, false, false, true, false, true, true. These statements mean the same thing. They have the same final column underneath their main operators, right? So since the columns are exactly the same, these two statements mean the exact same thing. So the answer is yes to are they logically equivalent. The final thing you can do with the truth table is you can test whether an argument is valid. So remember, an argument is when your premises and a conclusion. And you're trying to ask if the premises were true, would they support the conclusion necessarily? A valid argument doesn't have to be sound, that is, the premises don't have to be true. But if they were true, the conclusion would have to be true as well. What you can do is you can do a truth table for the entire argument, and you can look to see is there any possible way of making the premises true and the conclusion false. And the way you do that is by doing a truth table for the entire argument. So the argument, the way we write these when we do truth tables for them, we write them all horizontally in one line. We're going to separate each premise from each other with a semicolon. So this argument, P arrow Q, is the first premise. Semicolon just means I'm separating this premise from the next premise. That's not a logical symbol, it's just separating the one premise from the next. R arrow Q. Then the slash will separate the premises from the conclusion. The conclusion of this argument is R double arrow P. Now we're going to do a truth table for this. To do a truth table for this, we're going to count how many different letters there are in the entire argument. So when we count, we don't count how many letters there are in each statement. We count how many different letters there are in the entire argument. In the entire argument, there are 3 different letters, P, Q, and R. That'll tell us how many rows we need. Remember, when there are 3 different letters, we need 8 rows. So I'm going to count 8 rows here. For the first letter, you make the first half of the rows true, second half of the rows falses. If that same letter occurs somewhere else, even if it's in a different statement, you treat it exactly the same. So we make the P in the conclusion exactly the same as the P in the premise. And we move on to the next letter and reduce in half how many you did consecutively. So we did 2 T's and then 2 F's. 2 T's, so 2 T's, 2 F's, 2 T's, 2 F's for Q because we did 4 for P. Half of 4 is 2. So we do 2 T's, 2 F's, 2 T's, 2 F's. If Q occurs somewhere else, like it does in the second premise, we'll make that column the same as the column we made for the first Q. Now I move on to the last letter. The last letter you should always alternate TF, TF. So for R, we'll alternate TF, TF. Half of 2 is 1. So So we did 2t is 2f for q. We'll move on to r, we'll do half of 2, that's 1. That's alternating tf, tf all the way to the bottom. Once we have those filled in, we can fill in the tables for the premises and the conclusion. So true arrow true is true, true arrow true is true, true arrow false is false, true arrow false is false, false arrow true is true, false arrow true is true, false arrow true is true, false arrow false is true. So this is false arrow false is true. True arrow true is true, false arrow true is true, true arrow false is false, false arrow false is true, true arrow true is true, false arrow true is true, true arrow false is false, false arrow false is true. So this column here and this column here represents the truth or falsity of the premises. Now let's figure out the truth or falsity of the conclusion. True double arrow true is true, false double arrow true is false, true double arrow true is true, false double arrow true is false, true double arrow false is false, false double arrow false is true, this is false, true double arrow false is false, false double arrow false is true. So now we're going to ask ourselves, is it possible to make these premises true and the conclusion false? So we're going to look at each row. So in this row, the premises are true, but so is the conclusion. But in the second row, notice that both premises are true. So underneath the main operator for each of the premises are true, the conclusion is false. If it's possible for the premises to be true and the conclusion to be false, that makes the argument invalid. The argument is not valid. It's possible to make the premises true and the conclusion false, the argument is valid. However, if we went through every row, we couldn't find a row where the premises are true and the conclusion is false. That would mean that the argument is valid. It's okay for a valid argument to have false premises, but it can't have its true premises and a false conclusion. So let's do another one. This one has 3 premises. P or Q, if P then R, if not R then not Q, therefore R. So we're going to be 3 different letters, P, Q, and R, so we need 8 rows. The first letter will make the first half true and the second half false. If P occurs somewhere else, we'll make it the same. Now there's a P here. Move on to the next letter. So we'll do the first half of the first half true. So we did 4 and then 4, we'll do 2 and then 2. If R occurs somewhere else, we'll make it the same. Move on to the next letter. So we're doing 2, so now we're doing 1, T, 1F, 1T, 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 1F. There's another R here in the conclusion. Now we can fill in these tables. So true or true is true, true or true is true, true or false is true, true or false is true, false or true is true, false or true is true, false or false is false, false or false is false. You'll notice when you do these a lot, you get faster as you go, but you also notice patterns that emerge in the table, especially in the bigger tables. True arrow true is true, true arrow false is false, true arrow true is true, true arrow false is false, false arrow true is true, false arrow false is true, false arrow true is true, false arrow false is true. Now this one we have to do negations first. This negation goes on the R, so we'll do the opposite of the R column. This now applies to this Q here, so we'll do the opposite of the Q column. Now look at the 2 negation columns to get the truth or falsity of the arrow. False arrow false is true, true arrow false is false, false arrow true is true, true arrow true is true, false arrow false is true, true arrow false is false, false arrow true is true, true arrow true is true. That's the truth or falsity of the third premise. Now there's nothing to fill in for the conclusion, it's just a single letter. We're going to look to see if there's a row where all the premises are true and the conclusion is false. In this first row, premises are all true, but so is the conclusion. In the second row, not all the premises are true. It's okay to have a false conclusion if not all the premises are true. That would just mean that the argument's valid but unsound. This argument's still valid because of this row. It doesn't make it, just because some of the we have false premises here. Because we have false premises, it's okay for the conclusion to be false. Now let's look at the third row. Premises are true, but so is the conclusion. Look at the fourth row. Second premise is false, so that's okay. Look at the fifth row. All the premises are true, but so is the conclusion. Look at the sixth row. Third premise is false. Look at the seventh row. First premise is false. Look at the eighth row. First premise is false again. Now there's not a single row of this argument where all the premises are true and the conclusion is false. There isn't a single row where all the premises are true and the conclusion is false. That makes it valid. So the argument is valid. I'm going to do one more truth table here. It's for this argument here, which I decided to write in English. If there's a God and God created everything in the universe, if God created everything in the universe and everything in the universe is good, it's not the case that everything in the universe is good, therefore there's not a God. If you write this statement in symbolic logic, we get this. If G, then C. If C, then E. Third premise, not E. Conclusion, not G. Again, you need 8 rows because there are 3 statements here. Even though C comes first alphabetically, I do the first thing from left to right when I set up the table. So I do G first. Second letter is C. 2 T's, 2 F's for that one. 2 T's, 2 F's, 2 T's, 2 F's. And for E, I alternate TF, 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 TF. And we can fill in these tables. True arrow true is true, true arrow true is true, true arrow false is false, true arrow false is false, false arrow true is true, false arrow true is true, false arrow false is true, false arrow true is true. True arrow true is true, true arrow false is false, false arrow true is true, false arrow false is true, true arrow false is true, true arrow false is false, false arrow true is true, false arrow false is true. This is just the negation of the one next to it, just the opposite. Again, this is the negation. We want to look for a row where all the premises are true and the conclusion is false. In this first row, the third premise is false. In the second row, second premise is false. In the third row, the third premise is false. So is the first premise. In the fourth one, again, both the first and the third premises are false. In the fifth one, all the premises, the third premise is false. In the sixth one, the second premise is false. In the seventh one, the third premise is false again. In the last one, all the premises are true, and so is the conclusion. So we can't find a row. If we can't find a row where all the premises are true and the conclusion is false, that makes it a valid argument. I'm not saying this argument is sound, right? This is an argument about whether or not God exists. It could be a valid but unsound argument if one of the premises is false, but the argument is valid. There's nothing wrong with the process of reasoning. If the premises are true, the conclusion is false. Notice the only way this argument is sound is if the real world is this last row, where all the premises are true. Then the conclusion is true as well. But you can decide for yourself whether you think all the premises of the argument are true. All right? So that's it for today. Thanks for listening.